If you've been paying attention to the science news recently, you may have heard about the 2022 Nobel Prize. This year, the Nobel Prize was awarded for research done on click chemistry and bioorthogonal chemistry by researchers Carolyn Bertozzi, Morten Meldal, and Sharpless. The world of chemistry is kind of like Lego, where we use building blocks to make complicated structures. And how do we accomplish this? Well, we require the building blocks to come together to make the more complicated structures. So let's see this in action. As we can see here, the building blocks have added on to one another, or we can also say they've clicked onto one another. Now, what is more interesting is that we can add on to these building blocks prior to them attaching, and therefore we can make a much more complicated structure with them. Shown here is the green and orange building block combined together. What we also see is that the blue and purple building blocks have been brought closer together. Now let's say we always wanted the green building block to be on top of the orange building block in this order. Well, there is a bit of a problem. Sometimes it's also possible that we get the order reversed, where we have the orange building block on top of the green building block. Well, chemists also face a similar problem in the world of chemical reactions. Now, before we look into this problem in a bit more detail, we need to review some chemistry concepts. Shown here is an azide molecule. It consists of 3 nitrogen atoms that have been denoted with the letter N. Each nitrogen is colored differently for the ease of identification. The blue nitrogen is surrounded by 2 lines on each side. This is referred to as a double bond. Double bonds form when 2 pairs of electrons are shared between the 2 atoms. In this case, the blue nitrogen shares 2 pairs of electrons with the red nitrogen and also shares 2 pairs of electrons with the purple nitrogen. The red nitrogen is also attached to a generic molecule that we have depicted in blue. Some of the nitrogens also have a charge. The positive charge is indicated by the plus sign, and the negative charge is indicated by the minus sign. Now, what's interesting is that we can have these electrons move around and alter somewhat of the charge on the nitrogen atoms. Shown on the right is an alternative structure of the azide molecule, and this is the molecule that will be partaking in a chemical reaction that we will be discussing. Shown on the left is the compound that we saw previously, the azide molecule. However, on the right we have a newer compound. This is called an alkyne. The 3 lines represent 3 pairs of electrons causing 2 carbon atoms to bond to one another. This is referred to as a triple bond. Under high heat, the electrons from the red nitrogen will target the carbon atom. We call this a nucleophilic attack. Then, 1 pair of electrons from the triple bond will nucleophilically attack the purple nitrogen. Finally, a pair of electrons between the purple and blue nitrogen get transferred to the blue nitrogen. Now, depending on the orientation of the molecules, we can get 2 different structures. As discussed previously, this can be problematic. Remember, what we want is the green building block to be on top of the orange building block. However, in this case, we're also getting the orange building block on top of the green building block. In the early 2000s, researchers Sharpless and Morten Meldal performed the same reaction. However, this time they added copper to the reaction. The addition of copper also meant that heat was no longer required. The copper functioned as a catalyst. Catalysts helped to reduce energy needed for the reaction. In this case, we no longer required heat, which reduced the energy. However, the copper catalyst also ensured that we only got one structure, the one in which the green block was on top of the orange block. This reaction would go on to be called click chemistry, as it was easy as clicking 2 blocks together. Click chemistry can be characterized as reactions that are modular, meaning that we use building blocks to make more complicated structures. Click reactions are also high in yield, which means that we get the desired product or structure in large amounts. These reactions are also required to generate non-toxic byproducts, making it safer for the environment. Furthermore, the reactions should not react with water, something that is very difficult to do as water is a very reactive solvent. Despite all these breakthroughs that click chemistry provided, it had one major disadvantage, and that is that it could not be used easily in a biological setting. This is because copper can be toxic to the body in high amounts. To address the issue of copper toxicity, researcher Carolyn Bertozzi decided to keep the azide molecule. However, she changed the previously used alkyne to a cyclooctane. Notice that the cyclooctane still retains a triple bond. However, this time, the triple bond causes a lot of strain. In other words, the carbon atoms that are a part of the triple bond are held in an unfavorable position. Some of this strain can be removed by breaking the triple bond. Therefore, the desire of the carbon atoms to have a reduced strain is what drives the reaction to occur. Dr. Bertozzi would name this reaction bioorthogonal chemistry. Bioorthogonal chemistry allows for the azide and the cyclooctane to react selectively in cells within the body. This is very advantageous as cells are filled with many other reactive compounds. However, we can now ensure that these two molecules will only react with one another when they come in close enough contact. Bioorthogonal chemistry allows for us to image proteins, nucleic acids such as DNA and RNA, and also sugars that are found on the surface or within cells. Bioorthogonal chemistry can also be used in a drug delivery context. For example, we can inject a molecule into a mice with a tumor. This molecule will be attached to a drug. Then we can add on a secondary molecule. This secondary molecule will go on and click on to the first molecule that we've seen. After this click reaction has occurred, we can cause the drug to be released. Therefore, bioorthogonal chemistry has changed the way in which we conduct chemical reactions. We hope this video was informative for you. Thanks for watching and stay curious.